Why do we have seasons? If your first thought is that Earth gets closer to and farther from the sun, you're not alone. It's a common misconception, but it's not the reason for the seasons. While our orbit isn't a perfect circle, the distance variation is surprisingly small and doesn't align with our summer heat or winter chill. The real answer is far more elegant, and it's all about a tilt. Imagine a line running through the Earth from the North Pole to the South Pole. That's its rotational axis. Now, this axis isn't perfectly upright compared to our path around the sun. Instead, Earth's axis is tilted about 23.5 degrees. This tilt, known as our planet's obliquity, is the master architect of our seasons. And crucially, this axis points to the same spot in space, towards Polaris, the North Star. No matter where Earth is in its orbit, this consistent tilt is the key. Because of this tilt, the sun's most direct concentrated rays don't always hit the equator. That tilt fixes where sunlight hits most directly, the subsolar point. This is the single location on Earth where the sun is perceived to be exactly overhead, at a 90-degree angle to the surface. Think of it as the bullseye for the sun's energy. As Earth orbits the sun over the course of a year, this subsolar point doesn't stay put. It embarks on a slow, steady journey across the globe. The point slides from 23.5 degrees north latitude, the Tropic of Cancer, all the way down to 23.5 degrees south latitude, the Tropic of Capricorn, and back again. These tropics represent the boundaries of this solar migration. Only within this zone can the sun ever stand directly overhead. This movement is the fundamental driver of our changing seasons. When your hemisphere is tilted toward the sun appears higher in the sky at noon. This high sun angle concentrates solar energy, delivering more heat per square meter, like a focused flashlight beam. At the same time, the tilt gives us longer days, meaning more hours of sunlight to warm the land, air, and water. This combination of direct energy and longer days is what creates summer. Conversely, when your hemisphere is tilted away from the sun's rays strike the ground at a lower, more oblique angle. This spreads the same amount of energy over a much wider area, making it less effective at heating the surface. Days also become shorter, providing less time for the sun to warm things up. This combination of indirect energy and shorter days is what brings us winter. The tilt's effects are most extreme near the poles. The Arctic and Antarctic circles, located at 66.5 degrees latitude, mark the boundaries of these extremes. Inside these circles, the tilt is so pronounced that it can create periods of 24-hour daylight in the summer, the midnight sun, or 24-hour darkness in the winter, known as polar night. So, what about that distance change we mentioned? Earth's orbit is a slight ellipse, not a perfect circle. Our closest point to the sun, called perihelion, occurs in early January. Our farthest point, aphelion, is in early July. But the distance change is minimal. Earth is only about 3% closer at perihelion than at aphelion. For the northern hemisphere, our closest approach to the sun actually happens in the middle of winter. This small 3% variance in distance results in only about a 7% change in total solar energy received. While not zero, this effect is completely overshadowed by the massive energy shifts caused by the axial tilt. The changes in sun angle and day length are the true heavyweights in the ring. That small distance difference simply can't drive the dramatic swing between summer and winter. Sun angle and day length dominate. But there's another piece to the puzzle. If the longest day is in June, why are July and August often the hottest months? This phenomenon is called seasonal lag. The reason is that Earth's surfaces, particularly its vast oceans, don't heat up or cool down instantly. They have thermal inertia, meaning they store heat and release it slowly. After the summer solstice, even though the days are slowly getting shorter, the planet continues to absorb more heat than it radiates back into space for several weeks. Water's high heat capacity is a primary cause. It takes a tremendous amount of energy to raise the temperature of water. This massive thermal reservoir delays both the peak of summer heat and the deepest cold of winter, creating seasonal lag. This lag effect also explains why the two hemispheres experience seasons differently. The southern hemisphere is dominated by the vast, uninterrupted Southern Ocean. This huge body of water acts as a massive climate moderator, absorbing heat in the summer and releasing it in the winter. As a result, the southern hemisphere generally has milder seasonal extremes compared to the land-heavy northern hemisphere. These key moments in Earth's orbit have names. The solstices, in June and December, mark the points where one hemisphere is tilted most directly toward the sun, our tilt extremes. The equinoxes, in March and September, are the halfway points. On these days, the tilt is sideways relative to the sun, and the subsolar point crosses the equator, bringing nearly equal day and night to the entire planet. Looking at the bigger picture, even these factors aren't perfectly constant. Over millennia, slow, predictable wobbles in Earth's orbit and tilt, known as Milankovitch cycles, subtly tweak the amount of solar radiation or insolation we receive. These cycles include precession, obliquity, and eccentricity, and they operate on timescales of tens to hundreds of thousands of years, influencing long-term climate patterns like ice ages. Precession is a 26,000-year wobble that shifts when the seasons occur during our orbit. Obliquity is a 41,000-year cycle where the tilt itself rocks between about 22 and 24.5 degrees, altering the intensity of the seasons. And eccentricity describes the 100,000-year cycle of our orbit's shape changing from more circular to more elliptical. While these cycles are critical for understanding ancient climates, they don't affect the seasons we experience in our daily lives. So let's recap the science of seasons. It all begins with our planet's 23.5-degree axial tilt. This tilt is the primary control knob, determining the angle of sunlight hitting your part of the world and the length of your day. More direct sun and longer days bring summer's warmth. Less direct sun and shorter days bring winter's chill. The changing distance to the sun plays only a minor role, completely overshadowed by the power of the tilt. And finally, the immense heat storage capacity of our oceans creates a seasonal lag, delaying the peak temperatures of summer and winter. It's this beautiful interplay of celestial mechanics and planetary physics that shapes the rhythm of our year and the world we feel around us.